Welcome to Adventures in Math. In today's adventure, we explore the transcendental number e. Starting with thinking about a simple way to animate a basic video game, we find e emerges naturally from an infinite hierarchy of equal rates of change. We will find that the number e is less meaningful as a static value and that its true importance is dynamic, as the natural base of exponential growth. In its simplest form, exponential growth, or exponentiation, is just repeated multiplication of the same number, or what we call the base b, by itself n times, where n is an integer. For negative values of n, we write this as the reciprocal of bn, or 1 over b to the n. For the case of b to the 0, we have the convention that it is equal to 1. What about for values of n that are not integers? In this illustration, we can see the powers of 2 starting with 1/8 or 2 to the minus 3, progressing to 16 or 2 to the 4th. For now, we'll use our imaginations to fill in the rest of the curve so that we can see what exponentiation looks like. Later, we'll find that we can define this geometrically related to the area under a hyperbola. To understand e, we need to understand rates of change. To make things more concrete, we'll use physical motion as our analogy. Starting with position, written as x, we can ask how fast position is changing over time, or its rate of change. We call this the speed, velocity, or simply x prime. In turn, we can ask how fast our velocity is changing over time. We call this acceleration, or x double prime. We can continue the pattern indefinitely. The next few are often called jerk, snap, crackle, and pop. In this illustration, we plot exponential curves and their first 6 rates of change for different values of the base b, starting with b equals 10. We can see that as we vary the base b from 10 towards the value of e, the rates of change start to align. When b is precisely equal to e, the infinite hierarchy of rates of change all become equal to the original curve, like watching planets align and continue in perfectly synchronized orbits. If we let b take on a value less than e, we can see the rates of change are no longer aligned, and if we go above e, the same is true. Now let's turn our attention to animating a basic video game. Though it's not obvious, we will see e emerge naturally in this context. Here we see the beginnings of a simple game involving firing a cannon. We would like to animate the ideal motion of the cannonball, shown as the red curve. To do this, we'll break the motion into time steps, approximating the motion with the same number of line segments. As we make the time steps smaller and smaller, we get more and more line segments, which approximate the motion better and better. At a certain point, we can no longer see a difference visually. We can implement this animation with a few simple update rules. First, we determine the value delta t, which is equal to the total duration of the animation, d, divided by the number of time steps, n. In practice, we will want to make n very large compared to d so that we get an accurate animation. We can update the motion for the cannonball animation with 2 rules. To update the position at each frame of the animation, we take the current position xt and add the current velocity vt multiplied by delta t, which moves the ball forward along a small line segment. For velocity, we do the same thing, except we add the acceleration at multiplied by delta t. In our case, the acceleration of the ball is constant, being equal to the acceleration of gravity in the vertical direction and 0 in the horizontal direction. What if we set all the rates of change equal to the position in the animation update rules? That is, at every time step, position is equal to velocity, which is equal to acceleration, and so on. This is similar to how we saw e originate earlier, and we will find it here if we keep looking. When all rates of change are equal, our animation procedure simplifies to just one update rule for position. Since velocity is equal to position, we can write xt plus 1 equals xt plus delta t xt, which is equal to 1 plus delta t times xt. If we continue to expand the right-hand side of the equation, we see a pattern emerge. We need to choose a value for the initial position x1, which needs to be non-zero or will never move. Let's set x1 equal to 1 so that the expression simplifies, And finally, let the number of time steps go to infinity so our approximation is arbitrarily accurate. At the end of the duration d, the true position is given by the limit as n goes to infinity. We have found a definition of the position where by construction all of its rates of change are equal, just like e raised to the d. Are they the same though? It turns out that they are the same because e raised to the d is the unique function with this property. We can prove this by assuming that another function has this property and apply the product or quotient rule to arrive at a contradiction. You may recognize the limit definition here since it appears when exploring continuously compounding interest as well. We have a definition for e raised to the d now, but we haven't found a way to compute it yet. We can use the binomial formula, which is in part defined by entries in Pascal's triangle. In this illustration, we see Pascal's triangle being constructed. We start each row and end each row with the number 1. The values in between are the sum of the two numbers above them. For example, 1 plus 1 is equal to 2. In the next row we see 1 plus 2 is equal to 3, and so on. When we want to refer to an element of the triangle, we say n choose k, meaning pick the kth element of the nth row. To make this concrete, let's see this in action a few times. First, we say 3 choose 2, and get 2. Now we say 5 choose 1, and get 4. Finally, we say 7 choose 3, and get 15. We write n choose k as parentheses with n above k and call it the binomial coefficient. This leads us to the binomial formula, which allows us to write 1 plus z raised to the n is equal to a sum over powers of z and binomial coefficient. From our exploration into animation update rules and renaming d to t, we find that e raised to the t is equal to the limit as n goes to infinity of 1 plus t over n raised to the n. We can apply the binomial formula here with z equal to t over n to find that e raised to the t is equal to the infinite sum of t raised to k divided by k factorial, where k exclamation mark is called k factorial and is the product of all the natural numbers up to k. For the special case of 0 factorial, we define it as equal to 1. Now we have a way to compute e to the t. It is possible to prove that this representation is faithful and converges for all real values of t. Let's set t equal to 1 to get e to the 1, which is equal to e. This way we can approximate e with more and more terms from the sum. With just a few terms, we're able to get a good approximation to e. In today's adventure, we found that exponentiation with e as the base is the unique function that has all of its rates of change equal to itself. We'll continue to explore e in our adventures, extending exponentiation beyond integers, finding a connection to the natural logarithm and the area under the rectangular hyperbola. If you enjoyed the video, don't forget to like and subscribe.